Hello, welcome to the lectures on the actinide chemistry. In this lecture series, we'll be discussing about the actinides, their relevance, and why one should be studying the chemistry of actinides. In this first lecture, I'll be discussing the introduction, discovery, and synthesis of actinide elements. The first question comes to our mind is why actinide elements? Because some of the early actinide elements like uranium and plutonium, they are having application in the nuclear fuel cycle as the fuels. The fissile isotope of uranium and plutonium, that is 235 uranium and 239 plutonium, can be used as a fuel material in the nuclear reactors. So that is why it is very, very important to study the chemistry of actinides. So first I will give some example now why this nuclear fuel cycle. Here I have given a schematic of the nuclear fuel cycle where we start with the uranium ore. So that is how it is, the mining of the uranium ore, and this also involves the mining of the thorium ore, because thorium can also give the uranium-233, which we'll be seeing in the course of this lecture series, that uranium-233 also is used in the ASWR reactors. So there it can be used as the fissile element. Uranium-233 is used as the fissile element in the ASWR reactors. So therefore, thorium dioxide and uranium dioxide, they are obtained from the mining and the milling operations. Then these elements and their compounds like the oxides of thorium and uranium, in this case the uranium oxide is given for fuel fabrication. Some cases, if you need enriched uranium, then enrichment is also one of the steps before the fuel fabrication. Then after fuel fabrication, it goes to the nuclear reactor, and after the nuclear reactor is operated for a certain period of time, then the spent fuel, where the fissile content has depleted significantly, is removed from the nuclear reactor core, and it is kept in a storage called the spent fuel storage, where the radioactivity is decreased the course of the time, and afterwards the spent fuel reprocessing is done, where the valuables like uranium and plutonium will be recovered. In case of the ASWR fuel, then we have to recover the thorium and also the uranium-233, and uranium and plutonium, they can be used as the mixed oxide fuel or the MOX fuel, and again it goes back for fuel fabrication and to the reactor. So this is the nuclear fuel cycle, or a closed nuclear fuel cycle, which we will be discussing subsequently in this lecture. Now, the chemistry of actinides, it is very, very important because of its application in the nuclear reactors. Also, after the nuclear reactor operation is over, the fuel is removed from the reactor core, and then, as I mentioned, there is something called the spent fuel reprocessing. There also the chemistry of actinide is important, where the uranium and plutonium is recovered using a process called Purex process, which we'll be discussing subsequently in one of the lectures in greater detail. Then the raffinate which is coming out of the spent fuel reprocessing is taken out for the nuclear waste management program, and there this actinides and the fissile products, they are vitrified and kept in the deep geological repositories. There also the chemistry of actinide is important. Mostly the minor actinides like americium, curium and neptunium, their chemistry one needs to know such that this nuclear waste management can be carried out very, very efficiently. Finally, there is also this effect of some of the hazardous actinides which are having large amount of radiotoxicity. Their effect on the environment is also very important to know. That is why one needs to study the chemistry of actinides. In such cases, the speciation and migration of actinides, mainly that of plutonium, one needs to understand. Now, apart from these application, the nuclear fuel cycle and also this environmental chemistry of actinides, it is also a challenging study where this actinide chemistry one needs to study because of their very interesting and challenging chemistry. Why it is challenging? Because of the high radioactivity of the actinides, their short half-life, and also one of the very important features of the actinide elements is their variable oxidation states and also very high radiotoxicity. In view of this, the manipulations in the laboratory is very, very challenging with the actinides. Now, what are the actinides? Now we know them as the actinide elements, and it appears that they are similar to the lanthanides, but about 80 years back, when these man-made actinides were not discovered, so that time it was not known which is the actinide series, and now we know that these actinides or actinoids, as they are called, they are F block elements where the electrons are filled in the 5f orbitals. The actinide series starts from actinium, which has this electronic configuration of 5f0, 6d1 and 7s2, and ends with lawrencium with the electronic configuration of 5f14, 6d1 and 7s2, and are considered to have similar physical and chemical properties of this. Mostly the later part of the actinides, they have the similar chemical properties and physical properties. Though actinium does not have any F electrons, it is considered part of the series similar to lanthanum in the lanthanide series. General electronic configuration of the actinides is given here. The outer core of radon is there, and you have this electron filling of these electrons in the S, P, D and F cells as given here. The electronic configuration will be discussed separately in another lecture. Actinides give rise to decay series such as the 4N, which is the thorium-232, 4N plus 1, that is neptunium-237 series, and 4N plus 2, 238 uranium, and 4N plus 3, that is 235 uranium series, which I am sure you have already studied in the schools. Now coming to whether these actinides are available in the nature. We know that these actinides like uranium, thorium, they are available in the nature in a very large extent, and also we know this actinium and protactinium also are available in the nature. But what about the other actinides like plutonium? They were not available in the nature, and they were synthesized around 1940 by Seaborg and in research group. However, interestingly, this plutonium was detected in the nature, and a trace quantity of plutonium was actually seen in the natural uranium-238 deposits such as one in the Oklo. This is called a natural fission reactor, was suggested to have existed in Oklo, Gabon, Africa. It was discovered by Francis Perrin in 1972, and this is the only location where this phenomenon of self-sustaining nuclear fission reaction is known to have occurred. This is thought to have taken place approximately 1.7 billion years ago and probably continued for a few thousand years. Now, why this was considered like this? This is because of the high amount of 235 uranium in that particular mine, which is maybe more than whatever we are seeing, maybe around 3.1% of 235 was probably existing at that time. Now it is much less than that, as you will be seeing in the subsequent slides. So one thing is that relatively large fraction of 235 uranium was existing in the ores. And secondly, There are also signatures of this fission, because the neodymium isotope monitoring was done for burn-up measurements, and from that isotopic ratios it was found out that definitely there is a change in this whatever expected from the normal, and that fissile fission, this neodymium fission product, this signature was seen. Then ruthenium 99 fraction was more, and also the reactor operated for several thousand years and stopped thereafter due to the lower 235 content and increased neutron poisons. So this suggested that plutonium was existing in this Oklo mines. Now coming to the periodic table, this actinides in the early part of the 20th century, the actinides were not placed in the periodic table the way we see them now. So they were considered as similar to the transition elements, so that we will be discussing subsequently. And as you can see that only actinium, thorium, protactinium and uranium were discovered by that time. So in 1913, Fuzon and Goering identified a short-lived isotope of protactinium with a half-life of 1.17 minutes while studying the uranium-238 decay. So this is how these actinides were discovered. First we will see the discovery of actinides. That is, the uranium is the earliest known actinide, known as early as 79 AD by the Romans, as its oxide extracted from pitchblende. It was also used as a coloring agent in glass in the Czech Republic during the medieval era, but the discovery of the element is credited to the German scientist Martin Heinrich Klaproth in 1789. The uranium metal was prepared by using Pelligot in 1841, and the atomic mass of uranium was then calculated as 120. Mendeleev arranged the then known elements in the periodic table and corrected the atomic mass of uranium as 240 based on its periodic laws. Coming to thorium, it was discovered by Morton Esmark in 1828 and Berzelius named it in 1829. Uranium and thorium are primordial elements, and 232 thorium starts the 4n decay series as mentioned, with the final stable product being 208 lead. Actinium was discovered in 1899 by Andre Debierne, and F. Ziesel identified and isolated the element actinium in pitchblende. In 1934, 500 mg of protactinium was isolated from pitchblende, but it can be easily formed now by irradiating thorium-230 by an N-gamma reaction, giving 231 protactinium, or thorium-232 by N-gamma reaction, giving 233 protactinium. So protactinium-233 is an important isotope as it is decaying to 233 uranium, which is a fissile element used in the ASWR reactors. Now the interesting thing is the discovery of neptunium. So Edwin Macmillan is the first to have discovered neptunium in the Berkeley Radiation Laboratory. In 1934, however, Enrico Fermi, he has published a paper suggesting the discovery of element number 93 after irradiating uranium with neutrons. So now Fermi believed very strongly that he has discovered a different element because it was giving a lot of radioactivity. Now this was disproved by Van Grosse, who suggested the possible production of protactinium, which was disproved later on, and Nodak, who suggested that uranium might have fragmented to 2 to 3 pieces of other radionuclides. This is, of course, before the nuclear fission was discovered. But Fermi stuck to his claim and he said that he has discovered element 93. At that point, though, which was to be similar to the group 7 elements, including manganese and rhenium. So as uranium chemistry is similar to that of molybdenum and tungsten, similar way the element number 93 was believed to be similar to that of manganese and rhenium, which are again transition elements. But the chemistry of the so-called element number 93, as claimed by Fermi didn't match to that of rhenium, and that is how this claim was proven wrong. Subsequently, the Japanese physicists Nishina and Kimura, they bombarded uranium with fast neutrons around 1940 or so, and they discovered uranium-237 with a half-life of 6.75 days. So this discovery was correct, but the amount of uranium-237 which was isolated by them was too less, because subsequently it was understood that uranium-237 decays to neptunium-237. But the neptunium-237 has a very long half-life, and also this uranium-237 decaying to neptunium-237 with a 6.75 day half-life. So the neptunium-237 which would have formed with a very, very less quantities, that is how Nishina and Kimura, they could not detect neptunium-237. Otherwise, they would have been the discoverer of this element. However, after the discovery of fission, Edwin Macmillan, he wanted to carry out some experiments to measure the fission yields of the uranium target in the cyclotron at the Berkeley Radiation Laboratory in 1939. So he carried out some experiments where he irradiated the uranium target by the neutrons coming from the beryllium target, bombarded by the 8 MeV neutrons in the 37-inch cyclotron. So he has used basically the thermal neutrons, and he has seen that this uranium target which he has used, basically a paper he has taken on which he has sprayed the uranium metal compound, and there he was irradiating with neutrons, and he found that this activity, actually what he did is he measured the profiles. Actually, he has taken several aluminum foils with around 0.5 milligram per centimeter square, this thick, and he measured the activity as a function of the range. Actually, the aluminum foils he has subsequently dismantled, and then he has measured as a function of this length or the centimeter in air, and he found this profile like this he has seen, and this is how he got. So this is actually decaying, so this is attributed to the fission products, and he found that there was a large amount of activity was still there. This is because of the aluminum foils. So subsequently what he carried out, some experiments he did where he taken a paper. Actually, instead of the aluminum, he has taken paper, and then he has stacked those papers, and then he found that very interesting trend he has observed. So he has plotted the activity as a function of hours, and what he has seen is that there is a fission product catcher. This activity is following this trend. This is a fission product catcher, and there was a 23 minutes half-life pattern was seen. This is the 23 minutes, and of course there was another one, 2.3 days half-life. So this was, so basically he has seen the signature of 23 minutes half-life on radionuclide and 2.3 days half-life another radionuclide. So this was rather intriguing. So he thought that there is definitely some new element has formed, but he wanted to prove it. How to prove it? So he carried out subsequently another experiment with the chemistry, and this will be the next slide. So this experiment, the chemistry experiment, was carried out by Emilio Segre, who is the discoverer of technetium, and Segre was an expert in the chemistry of rhenium. So when Macmillan approached Segre, so he carried out the chemistry of rhenium for this isolated radioactivity. What he did is he reacted with hydrofluoric acid in oxidizing conditions, and it behaved like a rare earth, concluding that it is a fission product and not a new element. So that is how the Macmillan, he thought that probably whatever he has discovered, it may be a fission product but not a new element. But after some time, he collaborated with Phil Abelson. And the same experiment he has carried out instead of oxidizing conditions in reducing conditions. And what he observed that there was a precipitation of this new element was possible, like thorium. So that's how he suggested that it is not a rare earth element and it is probably a different element. So then what he did, he repeated the experiment in oxidizing conditions and precipitated by sodium acetate. So then he got concluded that it may be similar to that of uranium. So finally, Macmillan, he concluded that the 23 minutes radionuclide is nothing but uranium-239, which is actually neutron activated product of uranium-238, which is present in the natural uranium, and the 2.3 days half-life radioactivity is nothing but a new element which is similar to that of uranium, and he named it as neptunium. So this is a reaction which is giving neptunium-239, that is 238 uranium captures a neutron giving 239 uranium, which undergoes beta decay giving 239 neptunium. Neptunium, subsequently this 237 isotope of 237 neptunium was discovered, but in that case the reaction can be twofold. It can be carried out by 235 uranium, which captures a slow neutron giving 236 uranium, and which again captures another neutron giving 237 uranium, which undergoes beta decay to give 237 neptunium. Another reaction is 238 uranium can react with fast neutrons giving 237 uranium plus 1 neutron. Then this 237 uranium again undergoes beta decay to giving 237 neptunium. So this is how neptunium was discovered. Now beyond neptunium, subsequently many other actinides were discovered. 238 plutonium was discovered by Sieber, Wall, Kennedy and Macmillan in 1940, and this was called as element 94, where the uranium was irradiated by neutrons from this cyclotron facility as the Lawrence Radiation Laboratory, and this was the first plutonium isotope which was discovered. Subsequently, of course, plutonium-239 was discovered by Seymour et al. Again by irradiating uranium with slow neutron, and this is the reaction. Uranium-238 which captures a neutron giving 239 neptunium, as already we have seen, and it undergoes beta decay giving 239 plutonium. So this 239 plutonium is very, very important. It is a fissile isotope of plutonium. It is used in our reactor, and subsequently it was used in the atom bomb. Now the production of heavier actinides. Between 1944 and 1974, 12 trans-plutonium elements were added to the periodic table, and element 95 and 96 were discovered, that is the americium and curium as we know today. They were discovered from the 239 plutonium. So the reactions are given here. Plutonium-239, when it is undergoing a nuclear reaction with helium-4, gives 242 curium plus neutron. Plutonium-239 can also undergo neutron capture reaction giving 240 neutron, 240 plutonium, which again captures another neutron to give 241 plutonium, which undergoes beta decay to give 241 americium. This 241 americium can also capture one neutron as given here to produce 242 americium, and this 242 americium can undergo beta decay to give 242 curium. So this is how this curium and americium were discovered by Seymour and his colleagues. And subsequently in 1949, the bombardment of americium and curium by helium ions accelerated by the 60-inch cyclotron. It produced element number 97, which is known as berkelium today, and element number 98, which is known as californium. The reactions are given here where americium-241 reacts with helium-4 to give 244 berkelium, and curium-242 reacts with helium-4 to give 245 californium. Subsequently, 1952, the thermonuclear explosion was carried out and it has indicated the formation of 253 californium. You see from here, that means a large number of neutrons are captured by uranium-238 to give uranium-253, which decays to californium-253, and this californium-253 subsequently decays to einsteinium-253. 255 fermium also was detected in this thermonuclear explosion, and subsequently in ORNL, this high flux isotope reactor, that is HFIR, was built with a neutron flux around 10 to the power 15 neutrons per centimeter square per second. A lot of these heavier actinides were synthesized using this high flux isotope reactor, and which is a transfermi of elements, however, was not possible, and they were subsequently carried out by some nuclear reactions, with some sort of fusion reactions were carried out, which we'll be discussing subsequently. Now, these are the isotopes of the actinide elements, as shown here from atomic number 89 to 103. As we see here, 89 is actinium, which was, of course, known before this synthetic actinide elements were produced in 1940. So thorium also was known, protactinium was known, and uranium was known, and from neptunium onwards, as I have mentioned, these were man-made actinides. And this number of isotopes are written here. You see, there are nearly 33 isotopes of actinium, starting from 204 actinium to 236 actinium, and mostly these are transient. They are not very stable isotopes. Thorium, there are 32 isotopes, starting from 207 thorium to 238 thorium, and the naturally occurring isotope, of course, is 232 thorium with a 100% observance. Protactinium, 30 isotopes are there, starting from 211 to 240 protactinium. Again, many of these are transient. Uranium, there are 27 isotopes, starting from 214 uranium to 219 uranium, then 221 to 240 uranium and 242 uranium. Out of these, the naturally occurring isotopes are given here, that is 234 uranium, 235 uranium and 238 uranium, with the abundance of 0.0055% for 234, 0.72% for 235, and 99.27% for 238 uranium. Now all these heavier actinides, starting from neptunium, they are man-made. Similarly, for the man-made actinide elements, the number of isotopes are listed in this table.